Okay, this is my video for inverse functions, and the first thing I'm going to do is talk about inverse functions and the relationship to the function. Inverse functions are more like inside-out functions. They're not really the opposite of the function. It's like inside out. Normally, it's like switching the x's and y's, is how it's usually described. But I'm going to talk about some of the characteristics of a function. Every function has a domain, and the domain would be your x values. And I'll put x in parentheses. The domain of the function, I have this big red equal sign because it is the same thing as the range of the inverse function. Likewise, the range, which will be your y's of your function, is the same thing as the domain of the inverse, which would be the x's of the inverse. So in other words, they switch. The x's of the domain become the y's of the range, and the y's of the domain becomes the x's of the range. The y's of the range become the x's of the domain. All right. The other thing that happens, because everything switches in an inverse, your x-intercepts, and sometimes they're called zeros. So I'm going to use that abbreviation for x-intercepts, and I'm also going to use the word zeros, are the same thing as the y-intercepts of your inverse. The y-intercepts of the domain will be the same thing as the x-intercepts, or the zeros, of your inverse. So in other words, I can put a double arrow because they just switch. So that's what it means when you're finding the inverse. You're switching your x and y's, and then these relationships occur. So these are some of the relationships that I'm going to go over in subsequent problems, because this is where a lot of the misunderstanding occurs. The first thing we're going to do is solve an equation for finding an inverse so you can better see what it means to switch the x and y's. All right, in this first problem, we're going to find the inverse of f of x equals x divided by 2x minus 7. So the first thing I'm going to do is to rewrite using y. Because f of x is just a fancy way of saying y. So my function is y equals x divided by 2x minus 7. All right? Once I have that, I'm going to switch my x's and y's, because again, when you're finding the inverses, you're switching the x and y's. So I'm going to switch or change the places of the x and y's. All right, so this becomes x equals y divided by 2y minus 7. All right, the next thing I need to do is solve for y, because we want to get y equals again. All right, so the first thing I'm going to do, I see a fraction, which is y over 2y minus 7. And to eliminate any fraction, you have to multiply both sides by the denominator of that fraction. So when I do that, I get x times 2y minus 7 is equal to y times 2y minus 7. The 2y minus 7's cancel, so I'm left with y. The next thing I need to do is to distribute. So when I distribute this x, I get 2xy minus 7x equals y. All right. I'm going to go to the next page so I can write that. 2xy minus 7x equals y. So 2xy minus 7x equals y. All right, now I'm solving for y, but I have two terms with y in it. So I want those two terms with y in it on one side, and I want the one term with the x in it on the opposite side. So I'm going to move my y over here, and I'm going to move my negative 7x over here. When I do that, I'm subtracting y on both sides, so I get 2xy minus y. And then when I add 7x on both sides, it's equal to 7x. So now I have both terms with the y in it on the left side of my equation. Since I'm solving for y and y is common in both terms, I'm going to factor out a y. So I get y equals 2x minus 1 equals 7x. Again, keep in mind the goal is to solve for y. So now I'm going to divide both sides by 2x minus 1. And when I do that, I get y equals 7x divided by 2x minus 1. I'm almost done. The only thing that I need to do is write it in function notation. In function notation, because this is the inverse, it would be f to the negative 1, which is the inverse. That's your notation for the inverse function, would be 7x divided by 2x minus 1. And that would be your answer, and that's how you find the inverse of a function. All right, next we have questions that may ask you to find the range of the inverse of the function. Now you could go through the steps of finding the inverse and then determine the range from that, or you could use a shortcut which utilizes the knowledge that the range of the function has with the range of the inverse has with the domain of the function. And that would be that the domain, well, I'll say the range since we was talking about the range. The range of the inverse, and I'm going to use f to negative 1 of x, equals the domain of the function, which is f of x. So that means that what we need to find is the domain of the function. Now, since this is a rational function, that means to find the domain, we need to first figure out what can't be in the denominator. So to find the domain, we always look to the denominator, and you want to set the denominator equal to 0. So here we have our denominator is x cubed minus 8x squared plus 16x equals 0. So we're going to factor this because, again, we're looking for all those numbers that will make the denominator equal to 0, or in other words, makes this function undefined. So we're going to factor out an x because that's what's in common. That's the greatest common factor in all three terms. So we have x times x squared minus 8x plus 16. Next, we're going to factor this trinomial, x squared minus 8x plus 16. What factors of positive 16 add up to equal negative 8? And that would be a negative 4 times a negative 4. So we have x times x minus 4 times x minus 4 equals 0. So now we still need to find out what's going to make our denominator undefined. So you want to take each one of your factors and set them equal to 0. So this first one is pretty easy because x equals 0. All right, and then here these are the same things. So we only need to use one. X minus 4 equals 0, or x equals 4. So here the domain of our function would be all real numbers. So the domain of f of x is all real numbers except 0 and 4, which is also in interval notation, open parentheses, negative infinity to 0, then 0 to 4, then 4 to infinity. Now, our domain of the function is the same thing as the range of the inverse. So our answer is this, except I'm going to write it a little bit differently on the next slide. So our range of the inverse would be all real numbers, that's my R standing for all real numbers, except 0 and 4. And in interval notation, it would be from negative infinity to 0, from 0 to 4, and then from 4 to infinity. Okay, and again, the reason why we have this relationship, and I'm going to box this because this is really our answer, is because the domain of the function is equal to the range of the inverse. So what you want to do when you're given a function, you look for the domain of that function because that is the range of the inverse. Another word about interval notation, notice that I use parentheses for around the zeros and the 4 because parentheses mean not including. Because we don't want to include the 0 and 4 because it'll make the function undefined at those points. If I wanted to include the 0 and 4, I would use brackets, and brackets look like this. Okay, so that's brackets. This means include in interval notation. My parentheses mean does not include. And around the infinities, the negative infinity and positive infinity, we always use the parentheses because they extend on and on and on forever. All right, for the next problem, we're going to find the zeros of the inverse of the function. So here our function is f of x equals 2x plus 1 divided by x cubed minus 27. So one thing we need to remember is that the zeros, which are also x-intercepts, the zeros of the inverse equal the y-intercepts of the actual function. So this is what we have to remember when we're doing this particular problem. All right? The other thing we need to remember is how to find the y-intercepts. So I'm going to write the rule to find the y-intercept. And this, by the way, works for any function. You let x equal 0, and then you solve for y. All right, so on the next page, I'm going to show you how to do that using this particular function. All right, so our function again was f of x equals 2x plus 1 divided by x cubed minus 27. So I said we have to find the y-intercepts of this function because the y-intercepts would be the zeros or x-intercepts of the inverse. So we have to let y equal 0. So first thing I'm going to do is rewrite this in general form and not using function notation. So y equals 2x plus 1 divided by x cubed minus 27. All right, when I do that, I'm going to let my x's be equal to 0. So I have y equals 2 times 0 plus 1 divided by 0 cubed minus 27. 2 times 0 is 0, and 0 plus 1 is 1. 0 cubed is 0, and then 0 minus 27 is just a negative 27. So here, my y-intercept of f of x equals negative 127. This is also my 0 of the inverse equals negative 127. And this right here is the answer that I'm looking for. So again, this is another reason, another way that we use a relationship that a function has with its inverse to do a shortcut. You don't have to do so many calculations. All right. In this next problem, we're going to find the y-intercept of the inverse of the given function. And our function is f of x equals 7x plus 1 divided by 5x squared plus 3. Now, the one thing we have to remember, which is in our red little bubble there, is that the y-intercept of the inverse, and this should be negative 1 right here, equals the x-intercept of the function. All right, so whenever you want to find the x-intercept of a rational function, all you need to do is set the numerator equal to 0. So the x-intercept of a rational function set the numerator equal to 0 and solve for x. All right, so what I'm going to do on the next slide is just take my numerator, which is 7x plus 1, and set it equal to 0 and then solve for x. All right, so my numerator again was 7x plus 1 and set it equal to 0. All right, I'm going to subtract 1 on both sides. 7x equals negative 1. Then divide both sides by 7. X equals negative 1/7. So the x-intercept of the function equals negative 1/7. That means that the y-intercept of the inverse function has to also be negative 1/7. And that's our answer, and we're done. Again, it's just switching. All right, here's some concepts that are also being tested on this assessment. One is vertical asymptotes. And the way that you get vertical asymptotes is that you have to set the denominator equal to 0 and then solve for x. So here in my example, f of x equals x minus 4 divided by negative 4x minus 16. The first thing I'm going to do is set the denominator, which is negative 4x minus 16, equal to 0. All right, I'm going to add 16 on both sides, so I have negative 4x equals 16. And then I'm going to divide both sides by negative 4. And so x is equal to negative 4. So this tells me that I will have a vertical asymptote at x equals negative 4. So I will have a vertical asymptote, that's what VA is, x equals negative 4. Now, on the next page, I'm going to show you what that means with x equals negative 4. When you're graphing and you have a vertical asymptote, there will be a vertical line that your function will not cross. So if I have a number line, such as this one, and let's say this is -4. I'll let this be 4. All right, it means that at -4, you're going to have an imaginary line, such as this one. And you have a rational function. So your rational function may start here at -infinity and then go up and get closer and closer and closer to the asymptote, but don't touch it. And then pick up over here at the bottom, very, very close to it. And then it may turn and do something else like that. That's all that means. This is the vertical asymptote right here. And it's also a guide to help you graph the function. That's why the line is dashed. All right, so the vertical asymptote is the line that it will not cross. All right, the next concept I'm going to talk about would be the horizontal asymptotes. So here are the rules. When you're looking for the horizontal asymptote, you need to look at the degree of the polynomial that is in the numerator and the degree of the polynomial that's in the denominator. So the rules are, the first one would be the degree of the numerator is less than the degree of the denominator. When you have that, the horizontal asymptote would be the x-axis, or y equals 0. The second one would be when the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote is a ratio, and a ratio is a fraction of the leading coefficients. And then the third one, when the degree of the numerator is greater than the degree of the denominator, you don't have any horizontal asymptotes. You may have something that we call an oblique asymptote. And that's how you spell oblique. All right, so now I'm going to show you how to find the horizontal asymptotes and how you can tell. I'm going to use rule 1 and then show you rule 2 and then show you rule 3. All right. So for rule number 1, it says that the degree of the denominator has to be less than the degree of the numerator. So one example of that would be if you have something like 3x divided by x cubed minus 2x plus 1. In this case, the degree of the numerator equals 1. And the reason why I know that, okay, now it won't. Let's see if I can try again to write. Okay. Is it right? Okay, let's see. Okay, degree of the numerator is 1. That's because this exponent would be 1. It's the only one in the numerator. So, and that's the highest, so the degree is 1. The degree of my denominator is 3. Okay, and that's coming from here. Since that is the case, the degree of my numerator is less than the degree of my denominator, so that means that the horizontal asymptote would be y equals 0, which happens to be the x-axis. So that means that if you were graphing this particular function and you wanted to denote where the horizontal asymptote was, it would be a dashed line right on the x-axis, which means that your function will get very, very close to that horizontal line but not cross it. All right? That's the first rule, example of the first rule. The second rule is when you have the same degree. So let's say I have x squared minus 4 over x squared plus 5. Here, my degree of my numerator is 2. Okay, I'm going to say this again because I don't remember if I recorded it or not. All right, so here an example of the first one where the degree of the numerator is less than the degree of the denominator. Here I have 3x, and 3x, the degree of 3x is 1. So that's the degree of my numerator. X cubed minus 2x plus 1, which is in the denominator, the degree is 3. So here, according to my first rule, when the degree of the numerator is less than the degree of the denominator, then my horizontal asymptote is the x-axis, or y equals 0. So when you're graphing, it would be that dashed line on the x-axis that the graph will get very, very close to, but will not cross. All right. My next example, I have x squared minus 4 divided by x squared plus 5. Here, the degree of the numerator is 2. And the degree of my denominator is also 2. So since the degree of my numerator is equal to the degree of my denominator, that means my horizontal asymptote is a ratio of the leading coefficients. Here I made this one pretty easy. The leading coefficient here is 1, and the leading coefficient here is 1. So that means that this horizontal asymptote will be y equals 1 divided by 1, which is just 1. So if I was graphing, and this is 1, my horizontal asymptote would be going through here. And that would be my horizontal asymptote. All right, the last thing I'm going to talk about will be holes. Holes are places in the graph where you have a break, and I'm going to graph what a hole looks like. All right, in this particular function, these two functions here, they look very similar, but they look like they could be the same, but they're not. One has a hole and one does not have a hole. So here we're going to find out which has a hole. The first thing you want to do is whatever you see that is factorable, you want to factor it. You want to factor the numerator as well as the denominator. So over here where I have f of x equals x minus 4 divided by negative 4x minus 16, I see that my numerator, x minus 4, is already factored, meaning I can't do anything else with it. My denominator, however, negative 4x minus 16, can be factored because negative 4 is the greatest common factor of both negative 4x and negative 16. So I'm going to factor out a negative 4, and I'm left with x plus 4. All right, once my numerator and denominator are both factored, then I look to see if I can cancel anything out. That means if I have a common factor in the numerator and the denominator. Well, here I have x minus 4, and this is x plus 4. There's nothing in common, so I can't cancel anything out. And because I can't cancel anything out, this function has no holes. Okay? And again, a hole is a break in the graph. I'm going to write that up here. A break All right. Now, this function, we're going to do the same thing. If I look at this function again, the numerator cannot be factored, so it's just x plus 4. And because we've already done the factoring of negative 4x minus 16, we know we factor out a negative 4, and we're left with x plus 4. Notice I can cancel x plus 4 with x plus 4. So that's exactly what I'm going to do because that's the common factor in both the numerator and the denominator. So these can cancel. And when I do that, I'm left with 1 or negative 1/4. This means because I cancel, I have a whole at x plus 4, and I'm going to solve for 0. So x plus 4 equals 0. X equals negative 4. So that means at negative 4, I'm going to have a whole. That's what that means. This is my factor, x plus 4. That's where that came from. This right here. So at negative 4, I'm going to have a whole. So again, this first one had no holes. This one has one hole at x equals negative 4. Now, even though I'm not going to graph this particular function, I'm going to show you what a hole looks like in a graph. When you have a graph of any function, and it tells you that there's a hole at negative 4. So let's say we have a function that looks like a quadratic. Say this is our quadratic. Let's say this point right here represents negative 4. Well, right here would be our hole, because there's a hole at negative 4. That means there's a break in the graph. So I'm really going to try to erase this inside part, if it lets me. All right, and now I can draw my hole. So I have a hole at negative 4. So that's what a hole means, a break in the graph. All right, hopefully this video was helpful to you, and it'll help you to be successful on your tests as well as your upcoming exam.